Have you ever stopped to actually picture the invisible, lightning-fast logic happening right inside the devices we literally use every single day? I mean, whether you're tapping on a smartphone, typing away on a laptop, or, even just setting a modern microwave, there's this tiny hidden world of electrical pathways making all of those complex tasks possible. But how does it actually work?
Welcome to This Explainer. Today, we're going to take that cold, static metal of a microchip and translate it into a working, understandable brain. If you're the kind of person who loves to learn exactly how things function under the hood, you're definitely in the right place. We're going to break down the microprocessor step by logical step. Okay, let's dive into this. Here's our roadmap for today. We're going to start by meeting the microprocessor. Then we'll deconstruct the definition, map out the anatomy of a system, explore the execution engine, and finally, learn how to speak the chip's language. We're going from the macro physical chip all the way down to the micro binary language. Section 1, meet the microprocessor. To really grasp what this physical component is, we gotta look at its history. And here's an absolutely fascinating piece of trivia for you. There was never a mini processor phase. We leaped directly from the bulky, discrete elements of the late 1960s, which, by the way, were just way too large and way too slow, straight to the tightly integrated microchip of the early 1970s. All those separate components were suddenly packed onto a single piece of silicon. The size shrank by thousands of times, and the speed? It multiplied by several hundred. And just like that, the microprocessor was born. Now, before we get too deep into the weeds, we really need to clear up some terminology, because these three words get mixed up all the time. Think of it like a car. The microprocessor, that's just the engine. It's the silicon chip with the computing circuits. The microcomputer is the entire car. It uses that microprocessor as its engine, but adds external memory and input-output devices. And finally, a microcontroller is kind of like having a perfectly self-contained remote control car. It combines the processor, the memory, and the input-output all into one single package. All right, moving on to Section 2, deconstructing the definition. So here's the formal textbook definition. The microprocessor is a programmable device that takes in numbers, performs on them arithmetic or logical operations according to a program stored in memory, and then produces other numbers as a result. Now, I know textbooks can be super dense, but what's really interesting here is how we can unpack this exact sentence, word by word, to truly understand the chip's purpose. First up, programmable device. This basically means the microprocessor isn't rigidly locked into doing just one single chore. It performs completely different operations depending entirely on the sequence of instructions it receives. By simply changing the program, you completely change how the chip manipulates data. Its only real limitation is its specific instruction set, the specific group of operations it was physically manufactured to execute. Next up, we have takes in and produces. The chip desperately needs a way to talk to the physical world, right? So it takes in data from input devices like your keyboard or your mouse. Then, after it does its invisible math, it produces results, presenting them in a human-readable form on an output device, like the monitor you're looking at right now or a sheet of paper from a printer. But here's the catch. When it takes in those inputs, it's not seeing letters or colors. It only sees numbers. Specifically, binary digits, zeros and ones, which we call bits. The microprocessor actually has a very, very narrow view on life. It processes a specific group of these bits together as a single unit, known as a word. And the size of this word directly determines the chip's overall computing ability. To process huge amounts of information, the processor breaks data down into these bit groupings. A group of 4 bits, that's called a nibble. 8 bits is a byte. Now, early pioneers like the famous Intel 8088 were just 8-bit processors. Later came 16-bit chips, and groups of 32 bits were called long words. Today, of course, processors effortlessly manipulate 32, 64, or even 128 bits, all at the exact same time. Which brings us to Section 3, Anatomy of a System. Let's zoom out for a second. When looking at the macro system, right there in the center is the microprocessor. Data flows in from an input block, goes right into the processor to be manipulated, and then flows out to an output block. But notice that crucial connection to the memory block. The processor is basically helpless without it. It relies entirely on memory. Memory essentially serves as the holding pen for the chip's instructions and data. And it comes in 2 main flavors. ROM, or read-only memory, stores fixed information that simply doesn't change. RAM, or random access memory, stores user-supplied programs and data. If your computer ever suddenly freezes and loses your unsaved work, yep, that's your RAM getting wiped. Measured in kilobytes, megabytes, and gigabytes, memory provides the processor with exactly what it needs, exactly when it needs it.
Now, let's move in and see how this builds. Zooming closely inside the microprocessor itself, we find three main units. We've got the arithmetic/logic unit, or ALU, which does the actual heavy lifting math. Then an array of registers that hold data temporarily while it's being worked on. And finally, the control unit. All of this connects to the rest of the system via a completely vital pathway called the system bus. You can kind of think of the system bus as the computer's central nervous system. There are two incredibly vital electrical pathways here we need to understand. First, the address bus. This one is unidirectional. It only goes one way, out from the processor to identify a specific memory or peripheral location. But once that location is found, the data bus takes over. And that one is bidirectional, meaning it can carry the actual binary data back and forth between the memory and the processor. It's a beautifully synchronized dance. All right, section 4, the execution engine. So how do we breathe life into that physical, static architecture? Well, everything is powered by this incredibly simple, relentless 1-2-3 punch. First, the microprocessor fetches an instruction from memory. Second, it decodes or interprets that instruction. And third, it executes it. Fetch, decode, execute. That's it. This 3-cycle model repeats thousands, millions, or even billions of times a second until the entire program is completed. And finally, section 5, speaking the chip's language. Okay, so how do humans actually write the instructions that the processor fetches in the first place? First, I want you to consider this number, 256. This is the absolute maximum number of combinations an 8-bit microprocessor can physically recognize. Because a bit is just a 0 or 1, right? So 8 bits give you exactly 2 to the power of 8 combinations. It is a strict, hardwired hardware limitation.
But here's the thing, processors don't even use all of those combinations. Let's look at the classic Intel 8085 chip. It's an 8-bit processor, sure, but it actually only uses 246 specific bit patterns. And even more surprisingly, those 246 patterns translate to only 74 actual instructions. The reason for this is that a single instruction might have multiple different formatting requirements. These raw patterns are what make up the machine language.
Now, as you can imagine, typing out endless strings of zeros and ones is incredibly error-prone. Even using shorthand hexadecimal code, like typing 3C, is just way too difficult for a human to decipher on the fly. To solve this, developers created assembly language. They assigned a symbolic code or a mnemonic to each instruction. So instead of trying to remember the hex code 3C, a programmer just writes INRA to increment the accumulator register. Instead of 80, they literally just write add B. It perfectly bridges the gap between human thought and the chip's raw logic.
So, the absolutely crucial point here is that assembly language is completely locked to the physical design of a specific chip. Because companies like Intel and Motorola wire their logic units and registers completely differently, an Intel 8085 program absolutely cannot run on a Motorola 6800. No way. The mnemonics only make sense to a specialized program called an assembler, which automatically translates your human-readable add B right back into the raw binary that specific hardware requires.
We've gone all the way from the macro scale of memory and system buses, right down to the exact hex codes of an 8-bit instruction set. But computing never stands still. As we rapidly jump from those early 8-bit processors to today's massive 64 and 128-bit giants handling literal billions of cycles per second, it leaves us with one provocative question. Just how small and complex can these silicone brains ultimately get before we hit the absolute physical limit of technology? I'll leave you to ponder that one. Thanks for joining me on this explainer.